Hello everyone. In this video I am explaining arithmetic operations of the ARM processor, which includes addition, subtraction and reverse subtraction, and also a negate operation. So the general syntax will be of these instructions will be of this kind, so which includes opcode. That means it can take any of these mnemonics, and the condition, as we explained in the previous classes, the condition mnemonics are this, which can be included along with the opcode, along with this opcode, to make any of these instruction as a conditional execution instruction. So this suffix yes will going to update the CPSR registers or flags inside the CPSR register based on the outcome of the previous execution or previous instruction. So now we are going to use three registers, which is destination registers, and the two source registers. One of the source can be pre-processed by using a barrel shifter by doing a either rotation or shift operation. That's why that register has been mentioned with a name shift operand. So this is what condition is nothing but you can just include this one. So let's go to a program. So I've mentioned all the arithmetic instructions inside the program, and let's check how exactly the instructions will going to behave and what type of a flags it will going to update after the execution. So here I'm defined two types of a data, which is of one type of a data is of 32-bit wide and another one is a 16-bit wide. Since 16-bit wide data has been declared or defined in order to do a normal multiplication operation, which will going to produce the result of 32-bit wide. So for a long multiplication we are going to use two 32-bit data, which will going to generate a 64-bit result. Now let's come here. So I have just defined a two constant, which is called as a num and num1. So num1 will be defined as a defined using a assembler directive DCD, which means the define constant decimal. So where I have defined two 32-bit numbers. So these 32 numbers will be fetched to two registers. So first I am going to load the address of that constant to a register, then it will be incremented in order to fetch the second data. Now let's run the program and let's see how the instructions will going to be executed and generates the result. As you can I'll just okay, then I'm going to execute the first instructions, which will going to load the address of this constant num to the R1, so which is 6C. Again I'm going to, now this R1 is pointing to the first data, which will be fetched to the R0 register by using load instruction. Again I'm going to update increment this address 4 times, so that it will point to the next data. Why 4 times? You already know that ARM is a 32-bit wide, and each memory location will going to hold a byte size. So in order to point to the next data, in order to point to the next 32-bit data, I have to increment it 4 bytes. So that's why I'm just incrementing it 4 times in order to point to the next location. So now when I increment this, the address will going to get incremented 4 times. So now it has become 70. That means it will going to start pointing to this byte, that means 11. So now I'm going to fetch the second data and placed inside the R2 register. When I do, now we'll start with the arithmetic instructions. So the first instruction is add instruction, which will going to perform the normal addition operation. That means it will going to add the contents of these two source register and place the result inside the R3 register. But this as I have not used the suffix es here, as I mentioned in this document. So when I use the suffix, then only the CPSR register or the flag registers will going to get updated. Otherwise no flag registers will going to updated based on the outcome of the previous instruction. So now as I do the addition operation, as we can see, the MSB bit of the first operand is F and the second operand is 1. So if I add these two, definitely a carry will going to be get generated. But this, by executing this instruction, this carry flag, the carry that has been generated will not going to be updated or reflected in the CPSR register. As you can see here, I have just opened the CPSR register, which will have the 4 flag bits, which is N represented for a negative, Z for 0, C for carry, and V for overflow flag. Now let's see here whether the carry flag will be updated in the CPSR register or not by using that add instruction. As you can see here, only the register, only the result will going to be updated in the destination register, not the carry flag. So in order to overcome that problem, we are just using a suffix yes in the second instruction. I am just using the same operand and the same destination, so there will be no change here. Only the carry flag will going to be get updated here. See, now I'll just okay. As you can see here, the result will going to be the same, as the data is same and the destination is same. Only the difference between these two instruction is the second instruction will going to update the carry flag in the CPSR register. So now the third instruction is about the third type of addition that can be performed by using a carry flag. That means when I say ADC, that means whatever the source register, by not only the source registers will going to get added, apart from that, the whatever the value of the carry flag, that will also going to get added with the source registers, and then the result will be placed inside the R3. As you can see, the previous register just updated the C flag here, that means a carry flag here. Now the register, now as we know that these two operand will going to produce this result. When I put ADC instruction along with this data, the carry flag 1 will also going to get added and placed inside the destination register. That means that instruction will going to replace this value. That means it will make +1 here. That makes LSB as a 3. As you can see here, the carry flag has been added to the 2 of the source register, and then it has been placed inside the R3 register from this instruction. So this is the classes of the different classes of the addition operation, which means addition you can do just normal addition as well as the addition with carry also. And by using these suffixes, you can just update them. You can also use the yes here, so that if again the carry has been generated, that will be updated here. So it is up to you, it is up to the programmer whether to use a ADC yes or not. So let's jump into the subtraction operation. Again, this will going to do the normal operation as I did in the addition operation. So what happens here is the R2 will get subtracted from the R2, that means R0, that means R0 minus R2 will going to happen, and the result will be placed inside the RD, that means R4 register. Now these two are the source registers and this is the destination register. Again, as I am not updated the as I have not used the suffix yes, this instruction will not going to update the flag bits in the CPSR register. Only the result will going to update in the destination register. As you can see, these all ones subtracted, subtract this all ones, that makes it as 0 0, f minus 1 is e. So this is how the subtraction operation will going to have. By using this yes instruction, the same instruction will going to updated here. So if a borrow has been generated in order to subtract the second number, so if it is not, it will not going to update. This is how the subtraction instruction will going to have. So there is another class of a subtraction operation where you can do a reverse subtraction operation. So in a normal subtraction operation, what happens is the second operand will going to get subtracted from the first operand, but whereas in reverse subtraction it will going to do the opposite type. So that means R2 will going to subtract the R0, and whatever the result that will be obtained, that will be placed inside the R5 register. So here it was like R0 minus R2, but whereas in reverse subtraction R2 minus R0, that means second operand will going to subtract the first operand, and the result will be placed in the destination register. So again, it will also going to do one more thing. Along with the source operands, it will also going to subtract the carry flag. That means not of the carry flag, whatever the value that will be in the carry flag, that will get complemented and it will be subtracted along with these two operands. So that means that makes it as R2 minus R0, also the complement of C. If it is 1, it will be like 0 will get subtracted, or else it will going to subtract 1 here. So this is how the reverse subtraction will going to operate, and this is the reverse subtract carry. Along with the carry you can also subtract. The same thing will going to happen here. Here also there is no difference. And then I'll go for a negate instruction, where I'm just going to make the number as a negative. That means whatever the data that is present in the source registers will get subtracted from the 0, and that negative value will be placed inside the R6 register. For example, now in this register, R0 register, I have the value like F111. So I'm going to use a calculator so that you can easily understand. So I'm going to put that into an hexadecimal mode. So I'll just 0 minus F111 followed by 4 ones. So that makes it as a 32-bit data. So when I do 0 minus this data, you are going to end up with this result. So as you can see, as you perform the normal operation, when you do 0 minus any number, it will going to result with a negative of that number. So that negative of that number will be converted into a 2's complement, and then it will be placed inside the destination register here. So this is what it will going to do. So if I use a negate instruction, sorry, I have not executed that previous instruction. Now as soon as I do this operation or execute that instruction, as you can see here, so the result was same. So the lower 16-bit of the lower 32-bit of the data will be placed inside the destination register, which is of a 2's complement one, so which is equivalent to the negative number of that negative of this number. Then we'll jump to a multiplication operation. We have in multiplication operation we have two classes. We can just do a normal multiplication operation and a long multiplication. Normal multiplication means when you multiply two 16-bit numbers, you are going to end up with a 32-bit result. Whereas in long multiplication, when you do multiplication of a two 32-bit numbers, then the result will going to end up with a 64-bit. So the problem with the 64-bit result is, as we know, my registers inside the ARM processor is of only 32-bit. When you want to store the 64-bit result, you need to specify two destination register. Let's see how exactly it will going to work. First I'm going to make it for a normal multiplication operation. As you can see here, I have just defined two 16-bit data in order to generate a 32-bit result. So I'm going to load this address of this constant into an R1 register, as I did in the previous instructions. So I'm just going to add this number address, and I'm going to fetch. And remember one thing, I'm using LDRH. That means the boundary has been set to a 16-bit. So that means when you use LDRH, means half of the maximum size of the register will going to fetch. So since R0 is a 32-bit, half the size means that 16-bit. Now the 16-bit data will going to be fetched and placed inside the R0 register. As you can see here, that R0, the previous value, get replaced with this number, which is for 16-bit. So the lower 16-bit or lower part of this register will going to have this value, and upper higher bits will be cleared to 0. Again the same thing will going to happen with the second data. In order to point to the next data, I'm just using I'm incrementing it twice. Why? Because I did here 4 times, but I'm just doing here 2 times, because I just wanted to I was fetching a 32-bit data here, but whereas I'm fetching only 16-bit data here, so that this will take a 1 byte, this will take a 1 byte, so that makes a 2 bytes. In order to point to the next location, I have to just add 2 times, so that's what I'm doing here. So add just R1 to the R1 plus 2, that makes this 74 as 76. Now I'm going to fetch the second data, which is 4556 into the R2 register. So now I'm going to do the multiplication operation. As you can see, the two source register are this R0 and this R2. So these two values will going to get multiplied. Again, I'm going to use a calculator in order to make the calculations easy. So you are just multiplying this 4556 into 2, that will going to end up with a 8 AAC, and this 32-bit result will going to be stored inside the destination register R6. So R6 is, so the upper part is not, I'm not worried about, since I have not used the maximum value of the source register. The maximum value is like a FF and FFFF. So if you multiply this FF into FF, I'll just show you. This is the maximum value of a 16-bit. Again, the maximum value of a 16-bit, you are going to end up with this number. So this is the maximum 32-bit value in a normal multiplication operation that a register or a destination register can hold. So now, since my number was a bit smaller, it ended up with only a 16-bit. So this is how it will going to do a normal multiplication operation. So apart from that, I'm going to show you one more diagram. This is the ARM core data flow model, where in this block diagram you can see there is a one more unit which is called as a MAC unit, which is nothing but multiply and accumulate unit. So here what you are going to do is, apart from doing a multiplication, you are also adding the any other number to the result of that multiplication. I'll show you here. MLA. So now, so this is a destination normal 32-bit destination register. These are the two source operand as I used inside the used in previous instruction. Now this is the R0 register, which will going to whatever the value that is present in the R0, that will going to added with the result of after the multiplication of these two source register. Now the after addition of this content, that will be placed inside the R7. As you can see here, the content of R0 is 02. That means the 02 will going to get added up with this result, that is 8 AAC. I'll show you here again. I'm going to use the calculator. 56 into 2, that makes, this is the normal multiplication operation. Again, if you are using a multiplication and accumulate operation, that means you are just using plus R0 here. The contents of R0 is 02 here, so I'm just going to add plus 2 here. Now the result that will be stored inside the destination register is 8 AAE. So this is how the multiplication and accumulate operation will going to work. Let's execute this and see what the R7 register consists of. See, as you can see, the multiplication was like normal, but the contents of R2 get added with the result of the multiplication, and that will be placed inside the R7. This is multiply and accumulate. So this is about normal multiplication operation. When we want to, so in these two instructions, the result that was getting was limited to 32-bit. Now I'm going to explain how a 64-bit result that has been generated by multiplying a 32-bit number, and how exactly it will going to store inside the destination register. Now let's come back here. I'm going to use this constant in order to fetch the two 32-bit numbers. So first of all, I'm going to load the address of this num to the R1 register. As you can see, again it was 6C. So I'm going to fetch the complete 32-bit. I'm not going to use the LDRH. If I was using LDRH, that means only the lower part of this address will going to lower part of this data will be stored inside the R02. That should not happen. I need the whole 32-bit wide of data. So I'm going to use the LDR. That makes the data that is pointing by the R1 register has to be placed inside the R0 register. So again the first data has been fetched to the R0 register. Again I'm going to add it 4 times in order to point to the next location, as I explained in the previous section. Again it will get added 4 times, and now it is pointing to the second data, and the second data has been loaded into the second register, which is R2. Now I'm going to explain about the long multiplication. So this, if you add L to the MUL, that makes it as a long multiplication. Apart from that, you have to use one more letter, which is called as a U or S. So U means unsigned, S means signed multiplication. You can use it for a unsigned multiplication, and this SMULL can be used for a signed multiplication. So this represents unsigned multiplication for a long, unsigned multiplication long, and you can use 2 destination register. So each one of the destination register is of 32-bit. So that makes it, that complete destination makes it as a whole 64-bit. Now you are going to multiply these two numbers, which is of 32-bit into 32-bit, and your result will be like 64-bit. That 64-bit, and the lower part of the 64-bit will be stored in the R8 register, and the upper part will going to store in the R9 register. I'll show you with the example. Let me clear this one. So again I'm going to multiply the same data 111 into the second data was like 1111. So 1111 1111. So if you multiply these two, you are going to end up with a 64-bit result. Now the lower part of the result, that means a lower 32-bit result will be stored inside the first destination register. Whatever the register that you have mentioned as a first destination, the lower part will going to have, the lower 32-bit will going to store inside the R8 register, and the higher 32-bit bits will going to be stored inside the R9 register. Let's see. So R8 and R9 will going to hold the data. So when you do the multiplication operation, as you can see, 67654321. So 67654321, this lower part is stored inside the R8 register, and the upper part of the result, that means 10123456. So 10123456, this will be stored in the second destination register. So this is how you are going to do it. You can also use this instruction for a long multiplication for a signed numbers also. So now again I'm going to use the next instruction is all about the multiply and accumulate. So in the previous multiply and accumulate operation, I was just using one more register. So if the result is limited to 32-bit, now that time we can use a one more register, so that the contents to be added will be placed inside this register, and the whatever the result that is coming after the multiplication operation, that will be get added here and the store in the R7. But whereas I can't able to put one more register in this instruction, that means already I'm just using a 2 destination register and 2 source registers. I can't make it to the one more source register. So what happens here is, here also multiplication and accumulate operation will going to happen, but the data that I am not going to, the data to be added will not going to be mentioned in the separate register. Instead of that, so whatever the data that was previously stored inside the destination register, that will get added up with the R3 and R4. Suppose assume that you are going to have a data 001 and 002 in the R10 and R11 register. So now what happens is, you are going to add this higher bit. So this is R10, right? This is R10, that which makes here. So this lower byte of the previous multiplication will going to add it up with the this 1. So when you get this number, so plus 1 will be added here. I'll just copy that and I'll show you somewhere else so that it can be easily understandable. I'll take a document here. As you can see, I'll just separate it as a two numbers now. So this will be held by the first register, sorry, lower byte is stored in the R10 and R11. So this will be stored inside R10 and the higher byte will be stored inside R11, like R11. So now the previous content of the R11 was R2, sorry, 02. That makes this value get added up with plus 2 and this lower byte is 01, sorry, yes, 01. That makes the lower byte will going to get added up with value 01. So that makes it as do it here. So for higher byte, your value will be like 01, 01, 2, 3, 4, 5, 8, and the higher byte, sorry, lower byte will going to have the value 6, 7, 6, 5, 4, 3, 2, 2. Now let's check whether it will going to happen or not. See, after the, I'm just loading the value to get added into the destination register. So when you do this, as you can see, so I'm going to get a different value. So this is, maybe it is getting a value. So I'll come back to that with in a next video. So this is how we are going to do the arithmetic operation. So now apart from addition operation, or as I told you in the syntax, you can make this last operand as a shift operand. So you can just able to use the rotation and shift operation also along with this instruction. That makes it as R3 to get shifted by the logical left shift by 2 positions, and then it will going to get added up with the R2, and then it will going to be stored inside the R0. So this is nothing but a shift operand. So I'll call this source register as a shift operand. So this is all about the arithmetic operation instructions, where we will going to study about the different classes of addition, subtraction and the multiplication operation. So hope you understood. Thank you very much. If you have any doubt, you can feel free to contact me. Thank you very much.